Welcome everyone. For today's prep, I want to try another applied optimization problem. So we've already done example 1, and we're going to jump down to example 2. So first, let's read through this. And as we read through it, let's try to keep in mind, what kind of geometry are we going to be considering in this example? So we want to keep an eye out for just like geometric terms and things to help us draw our diagram. All right, so we're going to pretend we're the manager of a retail store, and we want to build a 600 square foot rectangular enclosure on the store's parking lot. And 3 sides are going to be used. We're going to use redwood fencing that costs $14 per linear foot. And then the 4th side is going to be a little more substantial. It's going to use cement blocks, which cost $28 per linear foot. And what we want to do here is we want to find the dimensions of the enclosure that minimize the total cost of the building materials. So, as we kind of read through this, well, the one key word that tips us off that we're dealing with an optimization problem is we see this phrase minimize. So that's immediately an indication that we're trying to optimize something. Okay. Well, let's think about what are we trying to optimize in this case? Well, we want to minimize the total cost of essentially building all these fences. So there's a few things we want to do. And it's going to kind of start us off by drawing a diagram. So a lot of times call this like step 0. Not always necessary, but it usually is a good idea, and it usually helps you get started. So let's draw a diagram. So we're going to be fencing in another area here. And, well, what kind of area are we going to be fencing? So we want to go back and look for, again, keywords that describe the geometry of this region. And we see, way back at the beginning, we're dealing with a rectangular enclosure. So that describes our geometry. So for step 0, let's draw our rectangular enclosure. And we know with a rectangle, opposite sides have the same length. So let's say the length of this side is x, which means the length of that side is x. And then we'll call this the length of those sides y. So we have our 2 variables. So rectangles generally have two variables, 2 dimensions. All right. So what do we know? We know that the area of this has to be 600 square feet. So while we're doing our diagram, we want to keep in mind what step 1 is of these applied optimization problems. That is, find the objective and constraint equations. So we want both of those. All right. Well, right with that rectangular, we see that the area of this is 600 square feet. So no matter how big x and y are, we want this area, the size of this rectangle, to be 600. So that means x and y just can't be anything. They have to give us, when combined in the correct order, they have to give us an area of 600. And in this case, the way we find the constraint to find the area of a rectangle, we multiply the 2 variables. So the area in this case we know is 600, and the area of a rectangle is length times width, so x times y. So that's our constraint. And usually the constraint involves some constant. So in this case, we're seeing a constant here, and it's telling us what the area has to be. Now, we do see other constants, so we can't just pick any constant, but usually you want to look for, one of the constants is usually a key to what the constraint is going to be. All right, so what's going to be the objective? And that's where we want to go to that keyword minimize. So we want to minimize the total cost. So the cost here, that's going to be our objective. All right, so we want to figure out how much is it going to cost to fence in this region. So we have to use this other info now to kind of help us figure out the cost. So it says 3 sides are going to use redwood fencing. So let's pick 3 of the sides. Doesn't matter which. So maybe let's say those 3 sides get the redwood fencing. And to build the cost, or to figure out the cost of building each of those sides, it costs $14 per linear foot. $14 per linear foot. So why is the length? Why is the number of feet? Say for this side here, why is the number of feet? And it costs $14 per foot. So to figure out the cost of building this one side, we're going to take how long it is, y, and multiply it by 14. And then same thing for this other side. Now this side has length x. So the cost of building this, fencing this side in, well, x is the number of feet, and it costs $14 per foot. So if, let's say x was 5. So that's giving us 5 feet here of length. Well, each of those is going to cost $14. That's what the per linear foot means. So if x was 5, it would be 5 times 14. But we don't know what x is yet. We got to figure that out. So the cost of that side is going to be 14 times x. And then same thing for the other side. Y is the length. And we know it costs $14 per unit of length there, per linear foot. So the cost of building that side is going to be 14y. Now, what about that missing side? Well, the fourth side here is going to use cement blocks. So we're going to be using something different over here. And this side costs a little bit extra. This costs actually double, $28 per linear foot. So the cost of building that other side is going to be 28x. Okay. So that is our objective. That is the function we want to minimize in this case. Now we can simplify this down. So let's simplify this down just a little bit. So the y terms here we can combine, and then the x terms we can combine. And let's just abbreviate this C for cost. So if we combine the x terms, we get 42x plus, and then we combine the y terms, we get 28y. All right, so that's our objective. And the constraint, the area we know is 600, so we can just write that as 600 equal x times y. All right, so this is usually the hardest part of doing these, is getting these 2 equations. Once we have these, now we just go through we go through the motions of our constrained optimization. So now, in step 2, this is where we want to solve our constraint. And we solve the constraint for one of the variables. So here, it doesn't really matter, so let's just solve it for y. So if we do that, we get y is equal to 600 divided by x. Okay. And then once we do that, we take that result and we plug it into our objective. So that's step 3. We plug it into our objective equation. So normally our objective, well, it has 42x plus 28y. Well, we're going to replace that y there with what we figured out, 600 over x. So we get 42x plus 28 times 600 over x. Okay. So now the benefit of this is now we have a one variable function. So we can use our regular optimization techniques of find the critical numbers and classify the critical numbers. So that's our next step. Step 4, this is kind of what we've been practicing. Now it's game time. So we want to find and classify the critical numbers. And we know with critical numbers, that means we got to do the derivative. So let's calculate C prime. So derivative of 42x is just going to be 42. And then derivative of this 28 times 600 divided by x, well, we can rewrite that if we wanted to. And you know what? If you want, you could multiply these together, but it's not absolutely necessary. If you're not sure, just leave them kind of unmultiplied. 28 times 600. And then this divide by x, well, we could write that with a negative exponent. So we could write that as x raised to the minus 1. All right, so if we differentiate this term, well, we do our power rule. We're going to take the negative 1, bring it down, put it in front. So we're going to get negative 28 times 600. Those are just constant multiples. And then x raised to the negative 2. Okay. Now we want to figure out where this derivative is either equal to 0 or where it's undefined. And before we do that, though, it's usually helpful to try and rewrite negative exponents back as a fraction. So if we do that here, we get 42 minus 28 times 600 over x squared. Okay. So we want to figure out where is this equal to 0 and where is it undefined? Or where does not exist? So we do see some fractions here. Now we have a couple options. We could try to get a common denominator, try to get this all into one fraction. We've done that before. But we do have a fraction. So we can look at just where that fraction divides by 0, where we have division by 0. And we see that that happens when x squared is equal to 0. So the derivative does not exist when x squared is equal to 0, which gives us x equal to 0. So that's one critical number. The next critical number, well, we're going to get a few more. We're going to set the derivative equal to 0 and solve this for x. So let's try that. So we're going to set 42 minus 28 times 600 over x squared. We're going to set that equal to 0. And then we want to solve this equation for x. So one thing we can do to try to get rid of that fraction, multiply both sides by x squared. And when we do that, we get 42x squared minus 28 times 600 equal to 0. So if we distribute that x squared, it goes to the 42. It cancels out the x squared in the denominator there. And then 0 times x squared is just going to be 0. And then finally, this kind of gives us something a little bit more recognizable in order what to do. Then we take the 28,600, move it to the other side, and divide by 42. So in this case, we end up with x squared is equal to 28 times 600 divided by 42. And then if we kind of do the division, there's a 6 hidden inside the 600, and there's a 6 hidden inside that 42, and there's a 7 hidden inside that 28, and there's a 7 hidden inside that 42. So we can, and 7 times 6 is 42, so we can cancel the 6's, and then we can cancel the 7's from the 28 and the factoring of the 42. And so if we keep going, we end up with x squared is equal to 400. And then when we do the square root, we got to get rid of that squared. So when we apply the square root, it cancels out, or we have to, that doesn't cancel out. Well, the square root cancels out the squared, and then we end up with x equals plus or minus 20. So it looks like we have three critical numbers here. We've got x equals 0, and then plus 20 and negative 20. All right, so we have our critical numbers, but only one of them actually makes sense for the problem. So let's think about it. What are we doing here? For this problem, we're trying to build a rectangle. So it really wouldn't make sense if the length of this side was 0. Wouldn't really have a rectangle then. And it really wouldn't make sense to have this side be length negative 20. So yes, x equals 0 and negative 20 are kind of relevant for the mathematics, but in terms of actually solving the problem, they're not. So we're going to throw these out for consideration because they don't actually make sense for the problem. So we want a positive value for x. Same thing here. And that's because length should be positive. We don't want negative length. We don't want 0 length. All right. So x equals 20 is the critical number that we're going to be considering here. So then to finish it up, we classify. So the classifying part, usually we do our second derivative test. That's usually the way to go. So we calculate our second derivative. And again, for the second derivative, it's usually better to use the one version with the negative exponent. So 42 is just going to be gone when we differentiate. And then we do power rule again, bring the negative 2 down. So we get positive 56 times 600, x raised to the negative 3. And then the way we do our second derivative test is we take our critical number, plug it into that second derivative, and see if we get a positive or a negative value. That's why it really doesn't matter too much about multiplying these out, because we can just tell positive, positive. So when we take our critical number, x equals 20, we're going to plug it into that second derivative. And in this case, we get 56 times 600, and then 20 raised to the negative 3 is also positive. So we don't really care what that number is exactly. We just care that this is positive. And if we think about what positive second derivative means, it means concave up. Draw the concave up shape. And that is a local min. So we found x equals 20. We confirm that it's giving us a minimum, and if we go back That's precisely what we wanted to find. We wanted to get a minimum for the cost. Now the question's asking for to find the dimensions, so that's kind of like the last thing, is just make sure that you actually answer the question. So let's answer the question here. So we found the x dimension. We just got to figure out the y dimension. And this is where we can go to where we solved our constraint equation. So we know x is equal to 20. And then we can use the constraint to get y. So y is equal to 600 divided by 20, which is our x value, and that is 30. Now, that's not quite the answer. We are given units, so we just want to make sure our answer includes units. So feet here. Okay, so these applied optimization ones, they take some practice. Generally, the hardest part for these is the setup. Once you get there, then it becomes a little bit more of has a kind of usual feel to it. All right, so we're going to practice more of these in class. So we'll see you then. Bye-bye.